In this video, we're going to talk about formulas to compute the surface area of some surface when that surface is described implicitly or explicitly. So I'm going to do implicit first. Imagine I have some function f of x, y, z equal to a constant, and that describes my surface. So I want to begin by trying to visualize the specific type of implicit surface I'm going to be talking about. First, I want to imagine that you have, say, the xy plane down here. Then what I'm going to imagine is that I have some surface which is sort of above this region in the xy plane. So, I don't know, maybe my surface looks a little something like this. That is, there's sort of this nice correspondence between the underlying region in the xy plane and the surface which is sort of sitting above it. Only sometimes can it be solved explicitly for a z as a function of x and y. Only sometimes can it be described as some region sort of sitting above a portion of the xy plane. Maybe better described as a portion above the yz plane. But I'm going to draw it as a representative like this. And I'm going to specifically take some point, I don't know, maybe this one right here. If I have the gradient vector, the gradient of my function f, this is just some normal vector that will be normal to the surface at that point. If I go straight down into the xy plane, there's another vector here. There's a vector that actually points straight up. That's the normal to the xy plane, which is the vector k hat. So now I get to tell you the type of surfaces I'm talking about. I'm talking about surfaces where that gradient vector and that k hat vector are non-zero. That is, there's no point where k hat is pointing straight up and the gradient, for example, is straight horizontally. I'm talking about one where the gradient of f always has at least some upwards component to it, such that this dot product is non-zero. And that is the sense in which I'm going to talk about my region of my surface being above the xy plane. We're going to see in a moment, this is going to be very important in terms of not having a denominator of 0 in the formulas we're going to compute. Now I'm going to talk about the assumptions a little bit more precisely. The first thing I'm going to assume is that I have a nice surface f. And what I mean by nice is specifically that it is what we call a smooth surface. To form the gradient of f, you're taking the partial derivative with respect to each of the different components. And what I'm saying is that those partial derivatives need to result in a gradient vector which is continuous. But in addition, I'm going to also demand that the gradient vector is not at any point the zero vector. But basically what I'm saying is that any patch of surface, there really is defined two unit normals, one sort of pointing up and one pointing down for any particular patch of surface that you have. There's no degenerate spots where the normal vector is just zero. I need that for my surface to be relatively nice. And then secondly, it was what we talked about previously. I want to think about this surface as being above a particular region down in the xy plane. And what I mean in that sense is that the gradient vector dotted with k hat is non-zero. So this is just to exclude the possibility that you have your xy plane down here and say, for example, you had a straight vertical surface where the gradient vector would be parallel to the original surface, would have this dot product of 0. Okay, so given those two assumptions, then we get our formula. Here it is. The surface area is the double integral over a region in the xy plane. So it's saying that I'm above a region in the xy plane. I can take an integral with respect to area in the xy plane, so a dx dy, and then my integrand is the magnitude of the gradient of f divided by the magnitude of the gradient of f dotted with k hat. And notice here in our formula how important it was that the gradient of f dotted with k hat was non-zero, because that's down in the denominator. Now, when we proved the analogous surface area formula for parametrically described surfaces, I spent a bunch of time on the derivation. I'm not going to do the same thing in this video. That is, I'm going to skip the sort of formal derivation as to why the surface area formula is true, but I do want to motivate it just a little bit. So one thing I want to focus in on is a contrast between two different scenarios. So in both scenarios, I have a square down in the xy plane, and then I have a surface that's living above it. Well, on the far left, I'm imagining that my surface is completely flat directly above the portion on the xy plane. So in this case, the length of the gradient f and the portion of the gradient of f that's in the k hat direction, those are just the same. And so this integrand is just 1, and integrating out the area along the base is going to give you the surface area. But in the second, that surface is now twisted. It would take more material to paper over that tilted surface than it would the underlying one in the domain. And so what we need to have is a stretching factor. And gradient of f divided by the length of the gradient of f dotted k hat gives us that stretching factor. Indeed, the more the plane is twisted, the more the gradient of f dot k hat gets smaller. And if it's smaller in the denominator, it's bigger overall. Basically, we've got a ratio between the original length of the gradient vector and then this portion of the gradient vector in the k hat direction. That is our scaling factor. Okay, so returning back to our statement with the assumptions, the actual assumption that it was over a region in the xy plane and that we were dotting it with k hat was actually a little bit arbitrary. In fact, I could replace this, and I'll replace it with a generic plane, where it could be the yz plane, could be the xy plane, could be the xz plane, it doesn't matter. And what I'm doing is replacing it with k hat with what I'll call a vector p, and p here is just I hat, or j hat, or k hat. As in, if you want to think of your region as a region over the yz plane and dot it with I hat, that's totally fine too. Or a region over the xz plane and dot it with j hat, that's also totally fine. For the most part, I just do it over the xy plane with a k hat. If it wasn't that, then you could just permute your symbols until it looking that way if you wanted to. It doesn't really matter, but I just wanted to note that this statement can be said with a little bit more generality. So that was our formula for implicit surfaces, but now I want to do a formula for explicit surfaces. Z is a function of x and y. And really what we're going to do is just say every explicit surface can be thought of as an implicit surface. So for example, I can come up with a capital F of x, y, and z, which is just f of x, y minus z equal to 0. So the level surface to capital F is just the same thing as this explicit surface. Okay, and now I'm just going to plug it into the formula that I had. So what's the gradient of big F? Well, it's the partial of little f with respect to x in the I hat, partial of little f with respect to y in the j hat, and then minus z turns into a minus 1 in the k hat. The length of f dotted with k hat is pretty simple. It's just length of minus 1, which is 1. And then the length of the gradient of f, square root of the sum of the components. So square root of fx squared plus fy squared plus 1. So our formula that we just were talking about is the double integral over the region of this fraction, the length of gradient of f over the absolute value of gradient of f dotted with k hat. And so just plugging those two things in, well, on the top I get the square root of fx squared plus fy squared plus 1. And on the bottom I just get 1, so I won't even bother writing it down. So this is our surface area formula for an explicitly described surface. And it's entirely up to you whether you want to have a new formula that you actually have to memorize every time, or if you only memorize the implicit and parametric, and when you're given an explicit formula, you just do the same trick we just did here and convert it into an implicit formula, whatever you prefer.